So what we have here is here's some of the original casing stones, and they sit on what's called a socle, which is this base, which was measured to be 55 centimeters in thickness. And of course, you got to bear in mind that this original slope casing stone, it wasn't stepped like that originally. It was a smooth profile. And so here you have, of course, here you see that the casing stones were damaged by the rubble falling down, but enough of them were still intact that one could make this accurate determination of the original angle. Here's the socle, which is 55 centimeters thick, and it sits directly on bedrock. So it actually, what it does is it creates two ways that one could measure the height of the pyramid, either with or without the socle. There's also two ways of measuring the base. This is a reconstruction from 1991 work on pharaonic stonemasonry. And this shows that outside the corners, which was the core masonry, there are these sockets. And I found one picture showing a socket. This is showing one of the sockets that's still there, that sits outside the core masonry. But based on those sockets, they were able to reconstruct what the original base of the pyramid would have looked like. So here would have been the 51 degrees, 51 minutes coming down, sitting on the 55 centimeter thick socle here, like this. Well, what this did was it gave two ways of measuring the perimeter of the pyramid's base. One could be measured from this point up on top of the socle. The other could be measured from down here that included the socle. So what you ended up with was two ways of measuring the pyramid's base. Well, which one was the correct one? Well, they were both correct. I think that they were actually intending to embody in there that there were two ways of measuring the pyramid's base. So what we have is the length of the base on the socle, which is the shorter of the two up there. It was varied from side to side. You'll notice 755 at the smallest to 756 just over at the largest. So there was some variation. There was probably a reason for that variation, actually, but we won't get into that because it just gets too technical for what we're talking about today. But the total of those measured around the four sides would be 3,023.139 feet. If you're taking notes, that'd be a good number to write down. Okay, so now let's see what the measure is around that includes the socle or the base. And we see that each side is roughly 5 feet longer, 760 to 761. Each side, again, is a little different, but we get a total of 3,043.433 feet. Okay, so I'm going to, over here, I'm going to write down a few numbers that we saw through our radius of the moon, diameter of the moon, radius of the sun, diameter of the sun, number of seconds in a day would be 43,200. Number of seconds in a half a day, number of seconds in a full day, 86,400. What were some of our other numbers? Oh yeah, 1440 was one, 7920. Diameter of the earth, just so they're up there in front of you, we can refer to them as we go on here. All right. So here is profile the Great Pyramid with a 51 degree, 51 minute angle. To make it easy, I've just rounded off the numbers, 481 feet in height. That would be not including the socle, the base. 755.85, I just picked one to use. And there's our 51 degree, 51 minute angle. And we find that when we measure it this way, it turns out to be almost exactly 11/7. There's some other interesting geometry going on related to the golden section, which I don't intend to get into today because it makes more sense if you're actually studying sacred geometry and you're familiar and you've made these drawings, because in a sacred geometry class, just like in the old Pythagorean and Platonic lodges, we draw, and then we eventually build models. And that's the way to really get familiar with this and get these numbers as part of your consciousness. So I'm not going to get into the connection with the golden section today. When we measure, including the socle, This becomes our height, 482.7575 feet, and the base, 760.9 feet. Okay, those are the numbers we're going to look at for a second here now. If we look at these are various estimates. We're looking at this one right here, the coal height estimate plus the sockle at 21.6 inches gives a total of the height above bedrock of 482.7575 feet. So now we're going to go back to the Earth so we can see how these numbers link the two. We take 1 square degree of latitude and longitude at the equator. Pretend we're standing at the equator. Okay, we know that the polar radius now is 13 miles less than the equatorial radius. So what that means is that the circle this way is shorter than the circle. The biggest circle that defines the Earth is the equatorial circle. So a degree of measure on the equator is going to be the biggest, the longest of any degree we measure anywhere on the Earth, the equator. Okay, the north-south is going to be a little bit shorter. And you'll notice right there, we've got 68.7 miles north to south and 69.17 east to west. So it's not a perfectly square unit, is it? It's a little bit distorted. Well, that distortion is totally significant because it's that distortion that is a measure of the Earth's departure from being a perfect sphere. And it's that departure of a perfect sphere that is very significant to us, because without that, again, Earth's orbital stability would be non-existent. Okay, so we're going to divide this up a little bit. If we take this square degree of latitude north to south, longitude east to west, and we look very carefully down in the lower right-hand corner, you're going to see something, a little square. You see that little square? That represents 1 minute, 1/60th of the degree this way, 1/60th of the degree this way. So that's 1 minute of latitude and longitude, all right? We're going to take a closer look at that, and we will see that 1 minute then is 6,045.881 north to south, 6,087 east to west, which is what we expect. The east-west should be a little bit longer, and that's 1 square minute of latitude and longitude. Okay, now we're going to divide each of those lengths into two. We're going to divide our square minute into 1/4 sections. And here's what I want you to notice. When we do that, we take 1/4 of a square minute of latitude and longitude. Look at our dimension east to west, and look at our dimension north to south. And look at these two numbers. In fact, here's an accurate calculation. We take the 482.755 feet, which is the height, and what we discover is that if we multiply that by the number 43,200, which is one of our sacred numbers that we've seen right there, 43,200, it shows up in the Vedas and the Sumerian king lists, etc., etc. If we multiply the height of the pyramid by that number, this is what we come out with, 3,949.83 miles. And notice the difference between the pyramid, which I call the standard polar radius, and World Grid System 72 is only 313 feet over the entire size of the Earth. So we have essentially the pyramid being a scale model of the Earth, the northern hemisphere, at a scale of 43,200 to 1. If we take the pyramid, enlarge it by 43,200, its height, including the sockle, now becomes the polar radius of the Earth within 300 feet of our satellite surveys. Then the two measures of the base are exactly the difference between the east-west difference and the north-south difference at a square minute at the equator. Now, the skeptic and the reductionist would dismiss this and say, it's just a coincidence, you're just playing with numbers. And I would say, okay, you can believe what you want, but it's there. The numbers are there. You can take the surveys of Egypt by Cole, you can take the geodetic surveys. I didn't make those numbers up, or I didn't fudge them. And what you discover is that when you expand it by 43,200, which, if the number was just some arbitrary number, but it turns out that the factor of expansion turns out to be one of the critical sacred numbers within the ancient systems. And so here we have the pyramid now enlarged by 43,200 times. And another way to think of it is if we go back to this diagram right here, you'll see that as the Earth turns, every half second, it's going to turn this far. So it means that every 2 seconds, the Earth, if you're standing on the equator, in 2 seconds, the Earth has turned 143,200th part of its total orbit. So if you're standing on the equator, in 2 seconds precisely, the Earth has turned a distance exactly equal to the distance around the base of the Great Pyramid. Now you can dismiss that as being coincidence, but the numbers don't lie. They're there. And so when William R. Fix was saying that someone somewhere thousands of years ago was able to measure the Earth with great precision, and I haven't, of course, elaborated upon all the details of this. I'm trying to give you the overall picture of how it might have worked. Referring back to our geodetic data, if we look at the various ellipsoids that give the polar radius, and then we take each of those polar radii, going from all of these ellipsoids down, the Clark ellipsoid has been the one of 1880, has been the one used in the United States for all non-military and non-NASA related measurements. We still use on a day-to-day basis. If you take a topographic map, and you're going out like a 7.5 quadrangle, and you're going out navigating with a topographic map put out by the U.S. Geological Survey, they're using the Clark ellipsoid right there. But you'll notice that when we take these various polar radii lengths in feet and divide them by 43,200, you can see the numbers we get right here. Remember, the height of the pyramid is estimated at 482.7575. So looking at this, what you'd see on here, which one would be the closest? Well, you notice it's come out very, very close to the satellite surveys. Given that it's very and see, when you got to ask yourself, well, why is there a difference between the satellite survey of 72 and the satellite survey of 80? Well, if we did another one again with as high a degree of accuracy, we would discover there's still going to be a discrepancy. And the reason is that the Earth spinning through space, there are various tidal forces working on the Earth which are constantly causing it to distort its shape by up to 2 or 3 or 4 or 500 feet. So we never would be able to get more accurate than 300 or 400 feet because the Earth itself is changing shape. And if we were to measure it every year for the next 10 years, we would get 10 different numbers. They'd all be very close, but they would deviate somewhat because the Earth itself, there are tidal bulges. Where's the moon relative to the Earth? That's going to affect. If the moon and the sun are on the same side of the Earth, that will affect the shape of the Earth up to being several hundred feet measured over the diameter of the Earth. And so it is not amiss to say that the pyramid enshrines a measure of the Earth that could be considered as accurate as those determined by modern satellite surveys. That to me is a very profound insight, because it does suggest that somebody, once upon a time, was able to measure the Earth size and shape with that level of precision. And if they were able to do that, what's the implication of that? See, that's the interesting part. Because no primitive culture, using the method of Eratosthenes in about 300 BC in Greece, he measured the Earth and was generally considered to be quite accurate because he was able to get the circumference of the Earth within about 500 miles of its actual measured circumference by using the methods available to the ancient Greeks, you see. And he was considered to be the first to measure by basically putting a stick in the ground in measuring the angle of the shadow on the longest day of the year over a couple of successive years. That's actually an exercise we do in the sacred geometry class because it's very interesting how he did that. But he was considered to be, pretty proficient because he was able to determine that the size of the Earth was, the circumference of the Earth was, 25,000 miles, when it's generally considered to be about 24,800, depending on where you measure it. So he was, maybe within 50 miles of the actual dimension of the Earth, but nowhere near as close as the pyramid would have been. So again, even if the pyramid was built 4,200 years ago, you got to say who 4,200 years ago had the technology to measure the Earth with that degree of accuracy. Now, that we know of, nobody 4,200 years ago did, or how they would have done it, we don't know. But on the other hand, if it turns out that the pyramid could be much older, it leads us back to the, going back 10,000 or 20,000 years. This to me is one of those little, sort of like the little crack in the dike, that if you don't keep it plugged, the whole edifice of contemporary knowledge could get swept away. Because we can't acknowledge that somebody 10,000 or 20,000 years ago was scientifically sophisticated. That was the days of Cro-Magnon man and Alley-oop living in the cave and so forth. Cavemen, which is a silly idea actually. Yes, I'm sure people did take refuge in caves when things got really crazy out here. Yes, I think people did take refuge in caves. But see, this is one of those things, again, that if you accept that it's not just a coincidence, it opens up a whole can of worms that mainstream science generally doesn't want to address. Because we're the epitome of scientific evolution right here and now, right? Nobody, before we built satellites, could have measured the Earth to within a couple of 100 feet of its actual dimensions. So, given 2 seconds of time, 143,200th part of the daily rotation, a point on the equator will travel a distance precisely equal to the perimeter of the Great Pyramid's base as measured with the socle. In 1/2 second of time, a point on the equator will rotate a distance equal to one side of the base of the Great Pyramid measured with the socle. So here you have a time and space measure integrated into one. The time measure comes in because it's the span of time that the Earth has moved. In 2 seconds, the Earth has turned and moved a distance within a fraction of an inch, being the distance around the base of the Great Pyramid. And so the height of the Great Pyramid measured with the socle is 143,200th part of the Earth's polar radius. So therefore, the Great Pyramid is a model of one hemisphere of the Earth at a scale of 1 to 43,200. So if we took the Great Pyramid and we created a duplicate and turned it upside down and put the two together base to base, that would now give us the polar diameter. And there's something else that's beyond the scope of today's talk, which we get into in an actual sacred geometry class. And this is looking how the pyramid is also the solution of the squaring of the circle, the ancient geometry problem of the classical world, the squaring of the circle. And that has very important implications for understanding the Great Pyramid as a three-dimensional map of the Earth. Because the Great Pyramid's square base is to its height exactly in the same relation as the radius of a circle is to the circumference of a circle. So you could picture that what's happening here, that means that in all maps you have a line of constant proportion, a line of where the scale, you know that all maps that you look at, there will be somewhere on the map where you have an accurate scaling. And as you move away from that line of accurate scaling, the maps become distorted. Well, if you've got a square and a circle of equal perimeter, you see, the Earth's equator, think of as the circle, and you think of this pyramid being enlarged 43,200 times, its square base is now the same distance around as the Earth's equator, right? So if you're mapping from the arc, the circular arc that's the Earth's equator, taking that and flattening it out, and now mapping it onto the base of the pyramid, the 43,200 times bigger pyramid, it's going to be exactly the same length. So there's going to be no distortion around the perimeter of the pyramid's base and the height of the pyramid, which is exactly the polar radius of the Earth. So that, from the standpoint of cartographic information, the particular geometry of the pyramid is very relevant because it is the solution to the squaring of the circle problem, which is something we studied extensively in a sacred geometry curriculum.